Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving into a fascinating paper. An algorithm for affordable vision-based GNSS denied strap-down celestial navigation. It's all about using the stars for drone navigation, even without GPS. Exciting, right?
Absolutely. GNSS denial is a huge concern. So how does this algorithm work, in a nutshell?
Basically, they use a camera to take pictures of the night sky. By identifying stars and knowing their positions, the drone can figure out its own location. But here's the clever part. It's a strap-down system, meaning the camera isn't stabilized. That's usually a problem, but they found a way around it.
I see. So no expensive, heavy stabilization equipment? That's a major advantage for lightweight drones.
Exactly. The key is that they make the drone fly in a circle. By averaging the position estimates from all points in the circle, they cancel out the errors from the unstabilized camera. It's like averaging out the noise.
That's ingenious. But how accurate are we talking? I mean, how big is the error margin?
They got position estimates within 4 kilometers. Not pinpoint accuracy, but considering the low cost and simplicity, it's pretty impressive, especially in a GNSS-denied environment, where other methods would drift significantly over time.
4 kilometers is still pretty good, especially for a low-cost system. But what about the initial alignment of the camera? Surely that's critical?
You'd think so, but they found that even with a significant initial misalignment, up to 90 degrees, the algorithm still converges to a reasonable position estimate. The orbital maneuver seems to correct for most of the initial errors.
That's remarkable. So it's robust to initial conditions. What about other challenges, like wind? Does that affect the accuracy?
Good question. They actually found that using GPS to maintain a precise orbit during their tests was detrimental. They got better results in simulations with a strong wind by simply maintaining a constant pitch and roll, letting the drone drift slightly while it completes the circle. The wind drift is less significant than the error reduction from the averaging.
Interesting. So the algorithm is more effective without GPS control during the orbit? That's counterintuitive, but it makes sense if the GPS corrections introduce more error than the wind drift.
Precisely. The key is the consistent yaw rate during the orbit, not the precise ground track. This is a really important finding for practical implementation.
This is really fascinating. It seems like this algorithm opens up some exciting possibilities for affordable, robust drone navigation in challenging environments. What are the limitations?
The biggest limitation is the need for a clear night sky. But they mention that future work could explore using infrared cameras to extend the system's usability to daytime or cloudy conditions. That would be a game changer.
Definitely. This research is a significant step forward. It's a clever solution to a critical problem. Thanks for breaking it down for us.
My pleasure. And that's all the time we have for today's Tech Bytes and News. Thanks for listening, and we'll see you next time. Goodbye.
Bye-bye.